Imagine a world where the rules of physics bend just enough to unlock entirely new technological possibilities. This is precisely what a team of researchers led by Professor Kai Sun from the University of Michigan is exploring. Despite his modest demeanor, Sun is a powerhouse in theoretical physics, driven by a passion for uncovering new fundamental principles and phenomena that challenge the limits of what we believe is possible. I primarily work with pen and paper, delving into analytical calculations, Sun explains. My interests span a wide range, but I'm particularly fascinated by phenomena that were once thought to be beyond reach. His latest research, published in the prestigious journal Physical Review X, does just that. It expands our understanding of quantum behavior, revealing that certain quantum states, previously thought to be rare, are actually more common and accessible than we imagined. Quantum mechanics, the branch of physics that governs the microscopic world, is notorious for its peculiarities. Unlike classical physics, which operates on clear-cut rules, quantum mechanics thrives on ambiguity. For instance, in the quantum realm, light and electrons can behave as both waves and particles simultaneously. Similarly, in quantum computing, qubits, quantum bits, can exist in multiple states at once, unlike the binary zeros and ones of classical bits. Sun and his team have discovered a new quantum state that sits in a gray area between two well-known states, localized and propagating waves. To understand this, imagine a rubber band. If you pinch it at 2 points and pluck it, you create a standing wave, a wave that remains stationary. On the other hand, if you flick the band, you create a traveling wave that moves along its length. These two scenarios represent localized and propagating waves, respectively. However, Sun's research reveals a third state that is neither fully localized nor fully propagating. This in-between state, characterized by a slower decay rate known as a power law, was previously thought to be highly unstable and difficult to achieve. But here's where it gets controversial. Sun and his colleagues have found that this state is not only stable, but also robust, requiring no fine-tuning to maintain. What we've discovered is a family of systems where all modes exhibit power law decay, and they are incredibly resilient, Sun says. This finding opens up new avenues for manipulating light and other quantum particles, with potential applications in quantum computing and beyond. One of the keys to this discovery was shifting the focus from one-dimensional problems to higher dimensions. By considering how waves behave in 2 or more dimensions, Sun and his team uncovered a phenomenon where power law decays are the norm near the boundaries of materials. They also found that the shape of the material, particularly its aspect ratio, plays a crucial role in this behavior, a factor that had been overlooked until now. And this is the part most people miss. The ability to reliably access these in-between states could revolutionize how we design and build quantum devices. For example, in quantum computing, qubits could use confined modes for local computations while relying on power law modes to efficiently transfer information between them. This work not only deepens our understanding of fundamental physics, but also paves the way for innovative applications, Sun concludes. As we continue to explore the bizarre and fascinating world of quantum mechanics, the implications of Sun's research are sure to spark lively debates and inspire further discoveries. Do you think the practical applications of these quantum states will live up to the hype? Share your thoughts in the comments below.